Chapter 15, Part 2. This is on the relative strength of acids and bases, so not actually finding a numerical value, just comparing acids and bases to each other. So the Bronsted-Lowry definition said that acids lose hydrogens and bases gain hydrogens. So it's a competition for the things that want to hold on to their hydrogen ions. So we can order acids in their strength as how easily they give up their hydrogens, or bases as how strongly they hold on to theirs. So if we look at this reaction, we have acetic acid and water. My acetic acid loses a hydrogen, so it's considered to be an acid. If we look at the reverse reaction, this H3O plus also loses a hydrogen, so it's also considered to be an acid. So if these acids are equal strength, the reaction is in equilibrium. However, one of them is stronger than the other. So in this case, because the H3O plus is a stronger acid, then this reaction is more likely to happen. It's more likely to give up the H than your acetic acid. So that's why the reaction is skewed towards reactants. It's not equal. If one is very much stronger, then it's not in equilibrium at all. It's just going in that direction. So we can rank acids and bases on a chart like this, from our strongest acid to the weakest, and then the same thing for your bases. Notice that these are in conjugate base pairs. So HClO4, the strongest acid, has the weakest conjugate base. And vice versa. The stronger the base is, the weaker its conjugate acid is. So they have this indirect relationship. Now, you do not have to remember, this is base, you don't have to remember this chart, you'll be given it, but you have to be able to use it to compare acids or bases in terms of strength. So if we have this given reaction here, sulfate and hydrofluoric acid, and they're going to form this HSO4 and F. So this SO4 turns into this turns into this. So if I'm reading in the forward direction, my HF is my first acid because it's losing a hydrogen. And then if we look at it in the reverse direction, my HSO4 is my acid. So that's my other acid. So if we look at these two acids we've labeled, our HF and our HSO4, on our chart, HF is weaker, HSO4 is stronger, which means it is more likely to lose the hydrogen. So it is more likely to go in this direction, losing the hydrogen, versus HF, which is weaker. Only few of them want to lose their hydrogen. Okay. Carbonic acid and HS, will they react to give any products? So if H2SO3, it can lose a hydrogen and form HCO3. Okay. HS will gain a hydrogen. Okay. I know that this is possible because if I did the opposite, so let's say I did H2CO3 as gaining, that's not anything on your list, but these two things are on our list. So this is going to be my acid, and then in this direction, this is also my acid. In this case, it's base. Okay. So if we look at those two acids, H2S and H2CO3, H2CO3 is slightly stronger, so that will go in this direction where it wants to lose the hydrogen better, and then a few of them will want to, your H2S's will want to lose as well. So two factors are what we use to determine relative acid strength. So the first is the polarity of the bond to which the hydrogen is attached. So all of these bonds are polar. Your hydrogen, it does not share electrons equally with whatever it's connected to. So the more polarized this bond is, or the bigger difference in electronegativity, the easier it is for that hydrogen to be removed, and therefore the greater the strength of the acid. So electronegativity, in case we have forgotten its trend, increases across a row, decreases down. So fluorine is the most electronegative element. The second factor is the strength of the bond, or how tightly it's held, and that depends on the size. So the larger X is, the weaker the bond and the greater the strength is. So as we go down a group, they get bigger, so therefore they get stronger in terms of strength. As we go across, we get smaller and therefore weaker. So these forces can oppose each other. So we have to consider which one's more important in the case-by-case basis. So if we look at binary acids, so H with just one other element in a given column. So as we go down, then our strength is going to decrease because your atoms are getting bigger. So that bond is getting weaker, which means my acids are going to get stronger because it's easier to pull away as we get stronger. So if we consider the elements F, Cl, and Br, and I in a given column, Hi is the strongest because it's the biggest, and then Br, HBr, HCl, and then finally HF is going to be the weakest. If we look at elements across a row, what we care about more is the polarity because their sizes aren't that different. They are smaller, but not a huge difference. So electronegativity increases across, which means your bond strength, or it's easier to remove that hydrogen, which means your acid strength increases. So as we go left to right, our acid strength also increases. So if we compare P, S, Cl, they're in a row. HCl is going to be the strongest acid. H2S is going to be your middle, and then H3P is going to be your weakest, since Cl is the most electronegative of those three elements. If you have an oxyacid, so oxyacid has this structure, H with an O and then attached to some atom. Bond polarity is the dominant factor that we look at in terms of their strength. And that determines, or that's determined by the electronegativity of whatever Y is. So if the electronegativity is large, then the OH bond is more polar, which means it's going to be easier to remove hydrogen, which means it's going to be stronger acid. So as we go down a column, then your electronegativity decreases, which means your oxo acid is going to get weaker. So if you have HOCl versus HOBr, this is going to get weaker as you go down. Okay. Other groups, such as O's or OH, may also be attached to the Y on the other side. As you get more O atoms added, then you get more and more electronegative. So that means the more O's you have, the stronger your acids get. So HOCl, really this is like this. That's really what the actual structure looks like. So we're talking about these O's added to the other side of chlorine. As we get more and more of them, right, we get more and more electronegative. So polyprotic acids have many protons, so that means they have more than one H that they can donate. Each successive hydrogen gets harder to remove. So the acid strength of an acid and its anions decrease as you get more and more electronegative or more and more negative charge. So in this first case, you have removing the first hydrogen, it's easier, then removing the second hydrogen, then removing the third, and then trying to remove, right, that's going to be weaker. So in summary, our general trends for a binary acid which has the structure H with just one other element attached. The two things that you're going to look for are the electronegativity of X so the more electronegative, the stronger the acid. The other thing you look at is the size of X. The larger, the stronger. If you have an oxyacid, which has H and then an O and then something, the more electronegative of Y, again, stronger. And the more oxygens you have, the stronger it is. So typically you're trying to look at what scenario you're looking at. If you have an oxyacid, you're going to be either looking at O's or electronegativity. You don't have to compare both at the same time. Or for a binary acid, you're going to be looking at electronegativity or the size. You're not going to have to gauge size of one versus electronegativity of another. That's a little bit trickier to do.